speaker, Professor Cecilia Clementi. Professor Clementi is the Einstein Professor of Physics at the Freie University in Berlin, but I believe she's joining us today from LA late at night. She's had a distinguished career. She obtained her PhD at CISA, the International School of Advanced Studies, one of my favorite cities, Trieste. She's been Professor of Chemistry for 19 years at Rice University before her current position. And she's been recognized with numerous awards, including a National Science Foundation Career Award and the Robert A. Welch Foundation Norman Hackerman Award in Chemical Research. So I'm very much looking forward to hearing about your work. And without further ado, Professor Clementi, the floor is yours.
Good afternoon or good evening, depending where you are. Thank you very much for the introduction. So I'll tell you something about what we've been doing recently to combine machine learning methods and more classical techniques in physics to try to understand the behavior of macromolecular systems. So to put things in context, I want to start by mentioning something that I guess many of you already heard, that is the fact that right now, since last summer, it's possible to predict the structure of proteins, even large and complex proteins, by using artificial intelligence with AlphaFold 2 from DeepMind. This news that this is now possible, that this algorithm can predict the structure of proteins from the sequence at a very good resolution, made the splash in the news. It was said that this is the solution to a 50-year-old grand challenge in biology. But if we put things in perspective, what this algorithm does is great, is really a revolutionary step in structural biology. But what it does, it gives you 1 point in the configurational space of a system, a variadimensional system like a protein. This is a particular point, is the folded state, is the most stable, energetically the most stable point in the overall energy landscape of the protein. But what we are interested in is the overall landscape, not just 1 point that is the most stable, the folded structure. That's a very important structure, is very important for development of drugs, very important for understanding the function of the protein, but nonetheless is 1 point. Instead, we are interested in the overall energy landscape, in understanding the overall configurational space. Why? Because proteins move around this point, and the dynamics of the proteins depend on the overall configurational landscape. Depends on how many minima there are, if there are barriers, how higher the barrier in the different pathways between the minima. This is a simulation I'm showing here on the bottom right, not from my group, from another group, showing a protein that moves through molecular dynamics. And as it moves, it populates different states, here represented by different circles that come into focus. And the function of this protein is expressed, the function of this protein depends on these dynamics. These dynamics determines the structure of this protein. So the overall landscape determines the dynamics of the protein, determines the overall behavior of the protein, the function of the protein. So this is extremely important to design vaccines or to design drugs, to understand processes like amyloid formation, enzyme functioning, and so on. So the most stable point that AlphaFold predicts is a great starting point, but it's just a starting point. What we need is the overall landscape. But of course, there is a huge problem here, the fact that in order to understand this dynamic, to sample the overall landscape, as already the previous speaker has mentioned, there is a time scale problem. It's not easy to sample the overall configurational landscape of a large protein because fast motions like side chain rotations, for instance, the localized fast vibration of certain bonds or around certain atoms is very fast, like femtosecond, but the motions we're interested in, like protein folding, is much longer, takes much longer, at least microsecond, millisecond, but can take much longer, like up slower than second. So it's impossible by computer simulation to cover this large range of time scales. And so we cannot do it by brute force molecular dynamics simulation. Our approach that is complementary to what the previous speaker has mentioned of speeding up the sampling, what we instead would like to do is to simplify the model, to try to design a model that is much less complex, the whole atom representation of the protein, but preserves the relevant physics, preserves the important features of the system. This is called coarse graining, and is a very is a very popular approach in physics, in many branches of physics, to simplify the problem as much as possible, but not too much, just to reduce the degrees of freedom that are not important for the behavior, the physical behavior of the system, but maintain the relevant physics. How do we do coarse graining? There are many different ways to do it. There are many different approaches. There is a bottom-up coarse graining. That means that we want to reproduce with the simplified model, with the coarse grain model, we want to reproduce the same behavior that we have with an atomistic model. So in a model with all the atoms, with all the details, we want to reproduce the same thermodynamics that they would have with the more complex model, but using a much more simple model. Or, and this is bottom up because we want to reproduce finer resolution, the thermodynamics or some properties of finer resolution model. We take the ground truth, an atomistic model. There is also top-down coarse graining. That means that instead we want to reproduce global observable thermodynamics or other experimental observable that are macroscopic, that are averages over the overall system. And this is top-down coarse graining, or there are other alternative approaches to, for instance, reproduce some structural features. This presentation, I'll talk about bottom-up and top-down, and eventually we'll try to combine the two approaches. So we want to design a coarse grain model, a simplified representation of the protein. Let's start with the bottom-up that reproduces the same properties, and we'll specify properties in a second, of a more fine-grained model by decreasing the resolution of the coarsening, increasing the coarsening of the model. The way we do it is through thermodynamic consistency. I don't want to go into the technical details, but it means that we want to reproduce the thermodynamics. If we want a model that is much more simple than the atomistic representation of the protein, but reproduces the same thermodynamics that we would have with an atomistic model. And there is a lot of theory developed in this context. And again, I'm not going through the details of the theory, but what I want to mention is that it's possible to, this is a well-defined mathematical problem, and it is possible to reformulate this question of finding an effective energy function, U, associated with the coarse grain model. It can reproduce the same thermodynamics of a fine grain model. It's possible to reformulate this question as a variational approach, meaning that we can associate a loss function to the problem. A loss function means that we can use, for instance, a neural network. to represent the energy of this system. So while historically a coarse-grained model was composed by a resolution and an energy function associated with the resolution. Resolution, for instance, instead of the overall protein, we consider only part of the atoms of this protein, and we associate an energy function, an effective energy function, to this representation that can reproduce some physical property. And historically, this energy function had an analytical form with like local terms, like terms that are associated with the stretching of bonds, stretching of angles, dihedral configuration, and so on, and non-local terms, an energy function, explicit analytical expression for the energy function associated with the interaction of residues that are not next to each other along the sequence. These are so-called non-bonded interaction. Now, instead of having an energy function, we have a neural network, because it's much more expressive representation of the interaction energy between these beads that represent groups of atoms in the protein. Why neural network? Well, because is much more, as I said, is a much more expressive representation for the energy, does not assume a functional form a priori, so it can represent a much larger range of possible functional forms, and is a very good way to represent complex, high-dimensional, and nonlinear and multi-body energy functions. And it allows to use the whole machinery of machine learning, like automatic differentiation and so on, to backpropagation and so on, to learn the optimal parameters. So this is what we proposed a few years ago in CGNet. The idea is to have, instead, as I said, an energy function for the protein, we have a neural network. The input are the coordinates of this reduced representation of the coarse-grained model of the protein, and the output is an energy, the energy associated with this coordinate. And this energy, this neural network is trained such that this energy function reproduces the same thermodynamics of some fine-grained model that we take as ground truth. So this is supervised learning. We learn to reproduce the thermodynamics of some fine-grained model, but using a much more simple representation for the geometrical structure, for the structure of the protein. So this speeds up calculation quite a bit, very significantly. This works very well. I'm going to show you the results for a small protein, signaling. This small protein is 10 residue long, but even if it's only 10 residue long, if you consider all the atoms in the protein, plus the fact that the protein is in water, if you consider all the atoms of the protein in the water, we have several thousand atoms, so several thousand degrees of freedom, while if we use our coarse representation, instead of all the atoms, we consider one bead per residue, and we have only 10 beads. So we go from several thousand degrees of freedom to only 30 degrees of freedom, the X, Y, Z coordinate of each bead. So this is a dramatic simplification in the representation of the protein. Now the question is to associate an energy function to this representation that can reproduce the same thermodynamics of this more complex representation that is given by first principle. And we use this neural network approach, CGNet, and it works very well. This is the results in this slide. Here in the top left panel, you find the ground truth, the atomistic model, free energy. If you have the free energy, you have the full thermodynamics of the system. The free energy here is expressed as a contour plot. Deeper blue means deeper free energy, lower free energy, that means more stable configuration. These are two collective coordinates. that express the configurational space, represent the configurational space of the protein. And the important thing in this free energy landscape is that there are three minima, these three blue regions. The first minimum, the deepest minimum A, corresponds to folded configuration, as shown here. The second minimum B corresponds to unfolded configuration, as shown here. And the third minimum C corresponds to misfolded configuration, as represented here. And indeed, if we use our model, we can find these three minima, and the structures in these three minima correspond very closely to the corresponding atomistic representation. But we have explored this landscape much more quickly, and a very small fraction of the time it would take to represent this landscape in atomistic representation. So this in the top right panel here, you have a control. If you get for this landscape, if you use a two-body representation, an analytical expression, as used, for instance, for classical force fields, for the interaction energy of the simplified model. And you see that you don't reproduce the three minima. So it's really this highlight the importance of using a neural network for this simplified representation. More recently, in the last couple of years, we've started to, this was shown here in this slide is a proof of principle, because the model that we developed here, the simplified model we developed to represent the thermodynamics of this protein, is made only for that protein, is model dependent, meaning if you take another protein, you will need to train another model to reproduce the thermodynamics, learning from atomistic simulation. So you don't gain much because you need the more expensive simulation to train a model to reproduce the more expensive simulation. But if you already have the more expensive simulation, there is no need of developing a simplified model to reproduce the same data. So what we really want is a transferable model. When we learn a model from a cheap simulation, and then we use it instead of expensive simulation for another protein that we cannot sample with atomistic representation. In order to do that, we borrowed this neural network architecture GNET that was developed by Tachenko and Muller in 2018, that is intrinsically transferable, because it's composed by pieces, it's like Lego, where each piece learns about a part of the sequence. So if you have a sequence of amino acids, this network is composed in a way that the interaction depends on the sequence. So if you have a different sequence, you can reuse the pieces of the network in a different order to reproduce the new system without training it from scratch again. And we showed, this is for the same protein signaling that I've showed you before, we showed that not only this works, but the error we make, and here we reproduce the error in reproducing the thermodynamics in two different ways. One way is the Kullback-Leibler divergence, that is the difference between the equilibrium distribution of the simplified representation of the coarse grain model and the all-atom model, or another way is the mean square error in the free energy. We showed that this SHGNet, that is the transferable architecture, makes a smaller error with respect to SHGNet, that is non-transferable architecture. So is more useful and also more accurate. And here is again the free energy landscape with the three minima, the folded, unfolded, and misfolded. And this is the ground truth the baseline simulation, what we want to learn. And this indeed is what is the model learning, and that the important thing is there are the three minima, and the configurations in the three minima match closely the corresponding ground truth, the atomistic representation. Here I'm showing you the dynamics of this protein. This dynamics is generated by the neural network. So instead of an energy function, in each step of the dynamics, there is a call of the neural network, and you see the protein folds as it should, and it stays folded. And if you wait long enough, it unfolds and then refolds. And in doing so, it explores the overall landscape, as it would do if the simulation was run with all the atoms. But this is run with a very reduced representation of the protein, a coarse grain representation, with this neural network for the energy function. We wanted to understand more why the neural network is able to represent so well the thermodynamics or more complex geometry, more complex representation, the neural network associated with the coarse grain model. And in order to do so, we designed a network architecture that mimics a so-called multi-body expansion that is done in physics to understand the relevance of different multi-body terms. So like two-body interaction, three-body interaction, four-body interaction, and so on. So indeed, this network contains a part that is only two-body interactions, but very general, like splines. Then with the three-body correction, that is like only all the possible three-body interactions, four-body interaction, and so on. And we can analyze the different parts separately. So first we train a two-body network, then we add the three-body as a correction, then a four-body as a correction, and so on. And what we find here is that this convergence, the convergence of this series is extremely slow. We need up to 5 body interactions. For instance, here, if you look at the error in the KL divergence and the Kullback-Leibler divergence, CGNet is the reference, is what I showed you before, what we can do when we use a neural network with everything, all the possible interactions. So this is a fully connected neural network. If we have only two body, we make a very large error, as I showed you. If we have two body, means basically that we use only two body interaction. That is what you can well approximate with analytical expression like splines. If we add the three body correction, we reduce the error, but it's not as small as CGNet. For body, you reduce it even more, but you need to get up to 5 body to get to the error, the small error that is associated to CGNet. And you can see the same thing with the free energy mean square error. But this is surprising because usually people in the literature have discussed the possibility of adding just three body correction to analytical expression for two body interactions. But here we showed that three body corrections or even four body corrections are not enough. You need a much more expressive representation of the energy with the possibility of higher order interaction. And this is why the neural network works so well, because the neural network is agnostic on the kind of interaction that is the kind of body order that is in the interaction, and reproduces all of that at the same time. Instead, if you try with an analytical expression, you need to stop at the third order or so, because it's basically impossible to represent in a expressive way higher order interaction analytically. So this result calls really for the use of neural network or some sort of machine learning approach for the design of coarse grain model. This is again showing the results. So these on top is the free energy landscape we want to learn. This is the free energy of the protein as a function of two global reaction coordinates. This is obtained doing the expensive whole atom simulation. So this is the reference, the ground truth. And here I'm showing you, for instance, if you look at figure G, what you can reproduce with up to 5 body interactions. And you see it's very similar, is almost indistinguishable from the ground truth. Instead, if you use here in C only two-body interaction, you get something very different. Three-body is better, but still very different quantitatively from the ground truth and so on. So you need up to 5-body interaction to quantitatively represent the thermodynamics of the atomistic representation of the protein. Another thing we have done, we have used the same machinery to instead maintain the same resolution for the protein, but simplify, instead of using the explicit water, instead of represent the water that is essential for the functioning of the protein in atomistic detail, we remove the water, but we design a force field that mimics the behavior of the water without using the explicit degrees of freedom of the water. This is called the implicit solvent. So we change the energy function such that the protein behaves as if there was water, but there is no explicit water. This is called this implicit solvent. It's a technique that is used a lot in molecular dynamic simulation. But instead of designing again the implicit solvent energy function analytically, we use a machine learning approach. So we use a neural network for it, and we use exactly the same approach as I just showed you for designing a coarse-grained model. The difference here is that we use the machine learning as in addition to the energy function that is analytically expressed, that is the whole atom energy function for the protein, but the machine learning learns the energy of the water that is not present anymore and the energy of the protein-water interactions. This is the architecture we use, that is again a SNET architecture with some modification. This is published, so I don't want to go into the technical details, but these are the results again for the same protein, for signaling the same protein, the same small protein that is our test bed that I showed you before. And the important result here is that again in A, in the left panel, there is the ground truth, what we want to reproduce with these three minima, folded, unfolded, and misfolded. And this in B, in the second panel from the left, is what our network learns. That reproduces the same free energy with the three minima without simulating explicitly the water, but using the neural network to effectively represent the effect of the water, even if the degrees of freedom of the water are not there. As a control, here is the vacuum on the right. That means that if we don't put the water at all, not even in the form of a neural network, the free energy is not comparable at all with what we want to represent in A. If we in D, in the second panel from the right, is what you get if you use one of the state-of-the-art method, they call it generalized Born surface area. That is a method to represent, is the implicit solvent method to represent the effect of the solvent with an analytical expression for this free energy of solvation. It's called the energy of the water and the protein water interaction implicitly. And you see this free energy is very different from what you get, what you want to produce, the explicit solvent simulation, while our network in B does a very good job to quantitatively reproduce this free energy. And here I'm showing representation of the structures in the three different ensemble, unfolded, folded, misfolded, that are the three different minima in this free energy. On top is the reference, and on the second line is the structures that you pull from our model that are very similar to the reference structures. So far, I've talked about bottom-up coarse graining, meaning that we want to reproduce the same behavior as in an atomistic simulation. Now I'm going to tell you something about the top-down coarse graining. That means we want to reproduce that behavior of experiments, because eventually what we want to compare to or want to predict are real data, experimental data. So even if we have a good bottom-up model, eventually we have to compare it with experiments. How do we do that? So the idea is instead of first starting with the model, running on a computer and comparing with experiments through, for instance, using statistical mechanics to do some averages, we start with experiment and we design a model that can reproduce experiment. And this calls for some mathematically, this is done with inverse methods. And again, we use some machine learning approach. So we use a maximum likelihood representation, meaning that we formulate the likelihood for our model, our energy function, our model expressed by an energy function to reproduce the experiment as a function of the parameters of this energy. And then we change the parameters to maximize this likelihood. And we obtain the model that has the maximum likelihood to reproduce the experiments. The kind of experiments we use are, for instance, Freie data, so that can be obtained spectroscopically and that express, for instance, the relative distance of two points in the protein, two fixed points in the protein, for instance, the position of two atoms in the protein, the relative distance as the protein moves, so the distribution of the distances as the protein moves, or as I'll show you in a second, different kind of experimental data. So again, in a nutshell, how this procedure works. We have a set of experimental measurements we want to reproduce with corresponding errors. We have an energy function with the initial guess for the parameters, with a lot of parameters. It can be a neural network with all the parameters of the network. We have initial guess for the parameters. We run a simulation. We predict the same observable for which we have the experimental measurement. Then we express the likelihood as a function of the parameters of the model. And then we have, with the reweighting tricks, we change the parameters to maximize the likelihood, and we keep going iteratively. This is to show you that this procedure works. This is a control experiment. So this is done with the simulated experimental data to understand if the model, this is a feasibility test, and indeed it works. So the reference, what we want to reproduce is in black. The zeroth order model, that is the model we start from, these are coarse-grained models. The model we start from without tuning the parameters is in blue, and you see blue and black are very different distributions. But in red is the result of this maximum likelihood optimization, and you see that red and black overlaps very well. This was the proof of principle, as I said, using simulated experimental data. But now we are using real experimental data. For instance, here we have used NMR data to represent the dynamics of ubiquity, a protein ubiquity. And we showed that it's possible to represent to reproduce the experimental data with the coarse-grained model with an accuracy that is comparable to what we can do with atomistic simulations, or even better. More importantly, recently we started to use, using an idea that we published many years ago, we started to use with this approach free energy of mutation. So mutagenesis experiment. Experimental is possible to mutate a residue, to change a residue in a protein sequence and measure the difference in free energy upon this mutation, for instance, in the different minima of the landscape. And if we measure the difference in free energy upon mutation in the folded state, is called a difference in stability. This can be measured experimentally, and is a measure that is a data point that we can use in our modeling for this maximum likelihood approach. We can design a model that we can tune a model that can reproduce the same stability difference upon mutation. And to do this, we use, to represent mutation, we use perturbation theory, but this is just a technical detail. So we have tried this technique with different proteins. And the beginning, instead of neural network, we've used given functional form for the energy of this coarse-grained model for the different proteins. So the coarse-grain is at the carbon alpha level, meaning that to represent this protein, we keep only the carbon alpha atom for each residue. So we simplify, again, a very aggressive coarse-graining, we simplify the resolution quite a bit. And this is the result for ubiquity. And you see here on the right that indeed there is a very good correlation between the experimental data, this delta G is the free energy of mutation, and the calculated experimental data with our trained model. In blue, you see the initial model, the model that is not optimized with the initial guess of the parameter. And in orange, you see the result, the correlation between the experimental calculated free energy differences when the model is optimized with this maximum likelihood. And you see there is a very good correlation. So our model, even if it's a simplified model, because it learned from experimental data, can reproduce the experimental data very well. But if when we try for this other protein, that is protein B, even after optimization, we see that there is a very large discrepancy between the experimental free energy difference upon mutation for a certain range of mutation and the calculated ones. In particular, there are three residues, these three dots here, that cannot agree with experimental data. The calculated values cannot agree with experimental data. And if we look at these three residues, we notice that are exposed to the solvent. They are in the surface of the protein in the folded state. This is because we use a fixed functional form for the energy here. In this model, we use a fixed functional form and we tune the parameters. And what I showed you before is that it's very important because of these multi-body interactions that arise in the coarse graining. It's very important to use multi-body terms. So it's very important, it's essential to use a neural network or some form of multi-body interactions. So we change the energy function and we use a more flexible representation. We use, in this case, a barrier term to express multi-body interaction. We correct it. And indeed, with this change, we are able to train even with these 3 points. This is we call it hybrid model that is more expressive representation of the energy with this barrier term. And in this case, we can learn also these 3 points. And so we can show that again, we can have a very good agreement between the experimental data, the free energy upon mutation computed experimentally, and the calculated one with our coarse-grained model. So with this, I would like to thank the people who have done the work, in particular my group, my collaborators, and all the funding agencies, and all of you for your attention. Thank you.
Thank you very much, Professor Clementi. That was a very interesting talk. So we have time for some questions. So if you do have any questions, please feel free to type them into the Q&A box and we'll do our best to answer them. I might ask one to start us off. So one of the most commonly used coarse graining approaches is the Martini model with a fixed energy function. And I was wondering, I was thinking about the early part of your talk, how your bottom-up sort of trained models compare to sort of one of the more established fixed energy functions.
So Martini cannot fold the protein. Martini is an energy function because of what I showed, because it's so important to use these multi-body terms, and Martini doesn't have them. You cannot take a protein for which you don't know the folded state and use Martini to find it. It's not able to do it. You need to have a folded state and restrain the simulation around this folded state, and then Martini can give you the dynamics. But it's not a predictive model for protein folding, for instance, because of these missing terms. So we showed in my work that it's essential to use this neural network or some other sort of eye-body interaction in these coarse-grained models.
Yeah, okay, that's really interesting. We've often wished we could use a coarse-grained model to look at conformational changes of protein, which obviously is very difficult with something like Martini, but maybe your approach opens the door to doing that.
Thank you, yes.
Yeah. I'll ask you another question that I had regarding the top-down models at the end. In that case, you start with an initial sort of guess of the interaction terms, and then you're improving them. How do you make that initial guess, and how important is it? If you choose something that's far away from the target, do you end up getting trapped in a different, sort of a different minimum?
So as you see here in these figures, for instance, there are error bars. These error bars correspond to starting from different points, from the different initial guesses. So we take that into account. We train not one model, but like 20, 50 models, starting from different random initial guesses, and we take into account the spread. And you see, when it works, the spread is small. When it doesn't work, the spread is very large. And this is also a sign that there's something missing. And indeed here, this is like a Martini-like model. There are no multi-body terms. When we add them, we are able to make it work.
And can I ask a very practical question, that when you're trying to implement this sort of machine learning interactions, how do you do it? As in, have you got it established within an existing code? Does it?
So right now we use our own codes that are available. By the way, we have in our paper we release the code. They can be interfaced. For instance, in this work, let me go back. Here, this is interfaced with the OpenMM. So at every OpenMM is used for the to compute the energy of the protein, to do the dynamics, but at every step you call a neural network for the energy, for the free energy solvation that is in PyTorch.
Great. We have a question from Rachuta, who says, nice talk and very informative. Has the coarse-grained model been applied to target fishing? If so, how well does it perform? And if not, is there a potential to explore this? Are you talking, Rachuta? I'm guessing she's talking about
drug design, I guess.
Drug design, yes.
So what I've showed you in this talk is the development of the models. We haven't used them for production yet because there are still some pieces missing. So this is for the dynamics of the protein per se. At the beginning, I said how the dynamics is important for understanding the function of the protein. That means also for drug design, for instance. But we have not developed yet models for the drug, to represent the drugs and the interaction of the drug with the protein in coarse-grained representation. So there is still some work to do before we can do drug design with this kind of models. We are, well, of course, that's our goal, but there is a way to go.
Okay, I don't think we have any more questions. So I'd like to thank you very much. It was a really interesting, informative talk, and thank you for staying up late to present it to us all. Thank you very much.
Thank you.